Welcome to Momentum, Knowledge in Motion, and this is episode 2. Today, we're diving into the fascinating world of large language models, LLMs, and their capabilities in common-sense reasoning tasks. To kick things off, let's explore the first paper. The paper titled QuestBench, Can LLMs Ask the Right Question to Acquire Information in Reasoning Tasks? Comes from the innovative minds at Google DeepMind, with contributions from Belinda Z. Lee of MIT. This research dives deep into how large language models, or LLMs, tackle reasoning tasks that aren't clearly defined, specifically focusing on their ability to ask the right questions to gather necessary information. QuestBench sets the stage by framing these reasoning tasks as constraint satisfaction problems, or CSBs. The key takeaway here is that while LLMs perform well in straightforward scenarios, they struggle significantly when faced with underspecified tasks, those that require them to ask clarifying questions to fill in the gaps. This gap in performance highlights a crucial area for improvement if we want to apply LLMs effectively in real-world situations. One of the standout features of QuestBench is the introduction of one-sufficient CSBs. These are designed to focus on acquiring just one unknown variable to solve a reasoning task. The researchers benchmark various problem types, including logic queue and planning queue, against state-of-the-art LLMs. The results are intriguing. LLMs show strong performance in grade school math problems, but face considerable challenges with logic queue and planning queue tasks. To dig deeper, QuestBench conducts ablation studies and correlation analyses. These studies assess how well LLMs can reason when they have enough information, and how adept they are at recognizing when they're dealing with underspecified problems. The findings reveal that while enhanced reasoning abilities can boost performance, there's a plateau effect, meaning that simply being good at reasoning isn't enough to tackle the complexities of information gathering across different problem types. A significant aspect of QuestBench is its approach to evaluating LLMs' information-gathering skills in these underspecified reasoning tasks. The researchers make a clear distinction between semantic ambiguity and underspecification, stressing the importance of models being able to accurately parse queries and identify missing variables to effectively solve CSBs. The paper formalizes underspecification in CSBs using a structured tuple that defines variables, domains, constraints, assignments, and target variables. It introduces a known predicate to assess what variables are known, establishing that a CSB is underspecified if the target variable remains unknown despite having known constraints and assignments. This framework emphasizes the need for efficient question-asking strategies. QuestBench also categorizes the difficulty of one-sufficient CSBs by analyzing various properties, such as the total number of variables and constraints, as well as the depth of the backward search tree. By employing brute force and backward search methods, the researchers provide a structured way to evaluate how efficiently LLMs can ask questions across different reasoning tasks. When it comes to the logic queue and planning queue domains, QuestBench defines specific properties and rules for reasoning tasks. In logic queue, the researchers create one-sufficient CSBs by withholding variable assignments to generate underspecified scenarios. Meanwhile, planning queue adapts the block's world domain, using predicates and actions to assess LLM's reasoning in dynamic environments, which is crucial for evaluating their question-asking efficiency. The planning queue dataset is particularly interesting, as it combines both one-sufficient and well-specified problems, focusing on the shortest action sequences needed to move from initial to goal states. This setup emphasizes the importance of identifying necessary questions to resolve ambiguities in the initial state, thereby enhancing LLM's capabilities in dynamic reasoning environments. QuestBench also develops the GSMQ and GSMEQ datasets, which consist of underspecified math problems framed as one-sufficient CSBs. These datasets are meticulously constructed through human annotation, ensuring high-quality CSBs by filtering out ambiguous or incorrect problems. This rigorous process sharpens the evaluation of LLM's ability to discern relevant variables amidst distractors, refining their overall reasoning capabilities. The evaluation results from QuestBench are telling. While LLMs perform well in the GSMQ and GSMEQ tasks, reaching a saturation point in their performance, they struggle significantly with logic queue and planning queue, often failing to exceed 50% accuracy. Interestingly, neither chain of thought nor few-shot prompting strategies seem to improve their outcomes, pointing to inherent challenges in these more complex reasoning domains. Now, let's get on to the second paper of this podcast episode. In the paper titled Benchmarking Systematic Relational Reasoning with Large Language and Reasoning Models, researchers from Cardiff University, including Irtaza Khalid, Amir Masoud Nourollah, and Schockaert, dive deep into the challenges faced by large language models, LLMs, when it comes to systematic reasoning. To tackle this issue, the authors introduce the Spatial Temporal and Reasoning (STAR) benchmark, a tool designed to rigorously evaluate both LLMs and large reasoning models, LRMs. The STAR benchmark is unique because it has a combinatorial structure that generates a wide variety of problem instances while ensuring that the dataset remains uncontaminated. One of the key critiques in the paper is directed at existing benchmarks, which often only test single-rule applications. This limitation means they fail to adequately assess models' abilities in multi-hop reasoning. In contrast, the STAR benchmark challenges models to learn and apply disjunctive rules across various problem instances, highlighting the need for advanced reasoning capabilities in AI systems. The complexity of reasoning with disjunctive rules is also a focal point of the paper. The authors explain that while this type of reasoning is more expressive, it becomes NP-complete when constraints are involved. The STAR benchmark incorporates both spatial reasoning, using the RCC-8 framework, and temporal reasoning through interval algebra, requiring models to deduce unique relationships by synthesizing information from multiple paths. The researchers investigate whether LLMs and LRMs can effectively apply composition rules provided in prompts, utilizing a compact integer encoding for both the composition table and the problem instances. They evaluate models in zero-shot, few-shot, and fine-tuned settings, revealing a spectrum of performance levels. Notably, models like QN and Gemma show particular strengths in these evaluations. The results are telling. Non-reasoning models, such as Meta Llama 3 and certain QN variants, struggle with accuracy on RCC-8 and interval algebra tasks, especially when faced with complex relational challenges. While some models achieve reasonable performance, they still lag behind neurosymbolic methods, which are better at systematic reasoning and generalization across diverse problem instances. The paper provides detailed performance metrics for various models on the STAR benchmark, highlighting that the O3 mini model shows impressive zero-shot accuracy, particularly with a configuration of B equals 1 /, where it achieves an accuracy of 0.9. A fine-grained analysis of the O3 mini LRM's classification scores reveals its performance on the K equals 9, B equals 2 dataset configuration. While fine-tuned LLMs excel in simpler tasks, O3 mini demonstrates some systematic reasoning capabilities, though it faces diminishing returns when tackling complex multipath problems, highlighting the ongoing challenges in AI reasoning. The authors also acknowledge the rapid advancements in reasoning models, suggesting that findings related to models like O3 mini may soon become outdated. They raise important questions about how well reasoning models can generalize to new tasks and stress the need for broader evaluations to better understand their limitations and potential improvements through fine-tuning larger models. Additionally, the paper references recent developments in enhancing reasoning capabilities through reinforcement learning, as seen in DeepSeek-R1, and discusses the rise of code intelligence in LLMs as explored in DeepSeek Coder. This intersection between programming tasks and AI reasoning adds another layer of complexity to the evaluation landscape for these models, indicating a dynamic and evolving field. Moving forward, we have our third paper to discuss. The paper titled WNOWHAT, a parallel corpus of paraphrased WINOGRANDE sentences with Commonsense categorization, comes from the CLPS research group at the University of Antwerp. It introduces an innovative resource called WINOWhat, which consists of paraphrased sentences from the WINOGRAN dataset. The findings from this study reveal that LLMs are not performing as well as expected on WINOWhat, which challenges the prevailing assumptions about their reasoning abilities. Interestingly, the research shows that there are minimal memorization effects at play, which suggests that we need to rethink how we evaluate common sense knowledge in natural language processing systems. One of the key contributions of this study is the identification of specific categories of common sense knowledge that are crucial for understanding and disambiguating sentences. This categorization allows researchers to assess LLM performance more effectively across different reasoning challenges. It also addresses a second research question about the particular difficulties LLMs encounter, thereby enhancing our understanding of their strengths and weaknesses in common sense reasoning tasks. Moreover, the study expands the evaluation of common sense reasoning tasks by translating them into multiple languages, including German and French. This broadens the scope of the research and allows for a more comprehensive assessment of LLM capabilities. Another important aspect discussed is the potential contamination in the Wino-Grand validation set, which could lead to underestimating the effects on benchmark data. This highlights the necessity for rigorous validation practices in evaluating LLMs. The study employs a meticulous paraphrasing and evaluation method, ensuring that grammatical accuracy and proper token placement are maintained. The results indicate that larger models, particularly LLMA 270B, tend to outperform smaller models across the various common sense categories. However, all models show decreased performance on paraphrased instances, suggesting that they may be relying more on dataset artifacts than on genuine reasoning abilities. This raises significant questions about the generalization capabilities of LLMs and the effectiveness of current bias reduction methods. The study presents accuracy results for a range of LLMs, including LLMA1, Pythia, LLMA2, Gemma 2, and OPT, across both Wino-Grand and WSC benchmarks. Notably, the performance gaps between Wino-Grand and Wino-What persist, indicating that there are deeper issues at play beyond mere memorization. The examination of dataset contamination reveals substantial implications for the integrity of model evaluations. Additionally, the study develops a parallel corpus to Wino-Grand by paraphrasing sentences in a way that positions the fill-in-the-blank token at the end. This new approach enhances the evaluation methods for common sense reasoning and highlights that all models struggle with these paraphrased instances, further questioning their true reasoning capabilities. The research also references significant prior work in coreference resolution and common sense reasoning, drawing on contributions from researchers like Yufeng Hu and Altaf Rahman. These foundational studies inform the current research, emphasizing the evolution of methodologies and the ongoing challenges in evaluating LLMs' reasoning capabilities across diverse contexts and languages. Next up, we'll delve into the fourth paper. In the paper titled Recitation over Reasoning, How Cutting-Edge Language Models Can Fail on Elementary School-Level Reasoning Problems, researchers from ByteDance Seed and the University of Illinois Urbana-Champaign dive into a critical issue: the performance of advanced language models on basic arithmetic and reasoning tasks. The study highlights a specific challenge. These models struggle significantly with subtle changes in math problems. For instance, when the wording of a problem is tweaked, the performance can plummet by more than 60%. This tendency to stick to established templates rather than adapt to new contexts is a major hurdle, especially in educational settings where genuine reasoning is crucial. Moreover, the researchers point out that existing benchmarks, like GSM-8K and Math, primarily assess models on STEM problems that can be solved through rote recitation. This focus exacerbates the performance issues, indicating a pressing need for innovative problem-solving approaches and a broader range of datasets that encourage real reasoning. To tackle these challenges, the study introduces the Row-R-Bench dataset, which includes 215 problem pairs, 78 math problems, and 80 reasoning problems. This dataset is designed to test the robustness of language models against unconventional answers, emphasizing the importance of rigorous problem formulation to enhance reasoning skills. When evaluating 23 advanced language models, including those using chain-of-thought COTI processes, the researchers found a concerning trend. These models faced an average performance drop of over 50% when dealing with modified problems from the Row-R-Bench dataset. Even the top performers, like DeepSeek R1 and OpenAI O3 Mini-High, struggled with more than a 60% decline in performance on these altered tasks. The study also explored the impact of forced correct prompts on vision-based problems, revealing that models still experienced an average drop of over 35%. This suggests that many models are overfitting to standard test cases, underscoring the necessity for a variety of problem types and innovative prompt engineering strategies to bolster reasoning skills. Additionally, the researchers investigated few-shot in-context learning, ICL, as a potential solution. While ICL showed some promise in handling original problems, the average performance gap remained significant, exceeding 30%. This indicates that ICL alone is not enough to bridge the gap, and further innovations are needed to enhance the reasoning abilities of language models in educational contexts. Even with the forced correct, prompt, and one-shot examples, models like GPT-4.5 Preview only achieved modest improvements, averaging 58.13% on no-solution problems. Many models, including DeepSeek R1, showed resistance to enhancements, highlighting the ongoing challenges in developing genuine reasoning capabilities. The study references various works that contribute to understanding the limitations of language models and potential pathways for improvement. It emphasizes the need for diverse datasets and innovative methodologies to enhance reasoning capabilities, ultimately aiming for more effective educational applications of these advanced technologies. As we continue, let's take a look at the fifth paper. The paper titled Brains versus Bytes, Evaluating LLM Proficiency in Olympiad Mathematics, comes from a collaborative effort involving institutions like Pennsylvania State University, New York University, City University of New York, Amir Kabir University of Technology, Bocconi University, and Autodesk. In this research, the authors dive into the performance of large language models, or LLMs, when tackling math Olympiad problems. They found that while these models can sometimes spit out the right answers, they often do so by recognizing patterns rather than applying logical reasoning. This raises a crucial point. We need better benchmarks that evaluate how well these models reason mathematically, not just whether they can arrive at the correct answer. With the introduction of advanced models like OpenAI's O1, there's a growing interest in improving reasoning capabilities through post-training techniques. The researchers evaluated these models against rigorous benchmarks like Olympiad Bench and Mathodyssey, only to discover that many existing assessments fall short in measuring the quality of reasoning. This has led to the emergence of a new method called LLM as a judge, which shows promise in accurately evaluating reasoning. Interestingly, some solutions generated by LLMs reveal fundamental misunderstandings, while others contain minor errors that could be easily fixed. To tackle this, the researchers propose a rubric-based approach to evaluate these solutions against established reference criteria. However, they caution that this method might miss valid solutions that don't align perfectly with the reference. The study also categorizes common logical fallacies found in LLM-generated solutions, creating a labeled dataset that annotates both correctness and the types of fallacies. This dataset is invaluable for verifying solutions and highlights the challenges advanced models face in distinguishing valid solutions from those riddled with logical errors, underscoring the need for improved reasoning assessments. To gather data, the researchers selected challenging problems from the International Mathematical Olympiad shortlist. 7 expert evaluators, including national-level Olympiad medalists and PhD holders, assessed the correctness of these solutions. The problems were designed to be original, multi-step, and solvable using high school mathematics, emphasizing the importance of nuanced reasoning over basic computational skills. While the research acknowledges potential data leakage from reputable IMO problems, it argues that this doesn't significantly affect LLM performance. Evaluators analyzed various cutting-edge models and identified common reasoning fallacies in incorrect solutions, such as proof by example and calculation mistakes, which undermine logical accuracy and validity in mathematical arguments. The evaluators classified solutions into three categories: correct, partially correct, and incorrect, based on their completeness and accuracy. They meticulously identified fallacies in incorrect solutions, recording both the model's final answer and the correct one. A thorough review process ensured that fallacy definitions were applied consistently, even in borderline cases, to achieve reliable evaluation outcomes. The results of the evaluation reveal a striking contrast between the accuracy of final answers and the overall quality of solutions across different models. For example, DeepSeek achieved a 63.2% accuracy rate for final answers, but produced no fully correct solutions. This discrepancy highlights the model's reliance on flawed heuristics, emphasizing the need for a more nuanced evaluation approach that prioritizes sound reasoning over mere correctness. Among the fallacies identified, inventing wrong facts emerged as the most common across multiple models, likely due to reinforcement learning that focuses on achieving correct final answers. Additionally, proposal without verification frequently appeared when models failed to justify their reasoning. The researchers noted variations in fallacy types across different mathematical topics, which significantly impacted solution quality. The analysis of these fallacies shows that the solution by trial and error fallacy is particularly common in algebra problems, while proof by example tends to crop up more in algebra, combinatorics, and number theory. This trend suggests that LLMs often validate propositions through specific instances rather than providing general proofs, highlighting a critical area for improvement in their reasoning capabilities. Now, let's transition to the sixth paper. This paper, titled Exploring LLM Reasoning Through Controlled Prompt Variations, comes from a research group at MIT, featuring authors Giannis Chatsavaroglu, Richard Yun, and Maura Kelleher. The study dives deep into the reasoning capabilities of large language models, or LLMs, using the GSM-8K dataset, which consists of 8,500 diverse mathematical problems. So, what exactly are these perturbations? The study categorizes them into four distinct types: irrelevant context, pathological cues, relevant context, and combinations of these factors. By systematically analyzing these variations, the researchers uncover critical insights into how LLMs reason and where their vulnerabilities lie. The researchers also reference the GSM symbolic benchmark, which is designed to assess LLMs' mathematical reasoning through controlled variations in problem statements. Their experiments reveal that LLMs often rely heavily on pattern recognition, and when irrelevant clauses are introduced, there's a notable drop in performance. This highlights the need for comprehensive benchmarks that can effectively evaluate the reasoning capabilities of these models. To assess the impact of perturbations, the study employs a systematic sampling process, selecting 56 representative data points from the GSM-8K test split. This allows for a thorough examination of how different types of context affect reasoning performance. The researchers found that when irrelevant and pathological context occupied up to 90% of the context window, it severely hindered the model's ability to navigate misleading cues. In their experiments, the researchers generated augmented prompts by appending pathological context to relevant information. They tested 13 different models, paying close attention to the limitations of context windows. The results were telling. Irrelevant context significantly impaired model performance, underscoring the urgent need for improved filtering mechanisms in LLMs. The study also challenges the assumption that larger models are inherently better at reasoning. Instead, it suggests that effective attention filtering and context prioritization might be more crucial for enhancing robustness across various reasoning tasks, regardless of the model's size or complexity. Some models even exhibited a death spiral, failing to respond up to 100% of the time when faced with irrelevant context. The researchers also looked into different prompting techniques, such as few-shot and chain-of-thought prompting. They found that certain perturbations could inadvertently encourage more structured reasoning responses. For instance, models like Command R+0, 8-2024, and Llama 323B Instruct Turbo showed that input context could act as implicit reasoning prompts, significantly influencing model outputs. Finally, the study emphasizes the importance of ethical considerations in AI development. It advocates for enhanced robustness and transparency in model design, urging a shift in focus from merely scaling models to improving their interpretability and addressing their susceptibility to context. This approach aims to foster trust in AI systems through comprehensive evaluation frameworks that take into account the societal impacts of these technologies. We're almost there. Here's the 7th paper. The paper titled, Have Large Language Models Learned to Reason? A characterization via 3 SAT phase transition comes from a collaborative effort between researchers at the Center for Applied Autonomous Sensor Systems in Sweden and the Department of Computer Science at KU Leuven in Belgium. This study dives deep into the reasoning abilities of large language models, or LLMs, by using the 3 SAT problem as a benchmark. The findings are intriguing. While LLMs tend to struggle with more complex instances of the 3 SAT problem, one model, referred to as R1, shows promising signs of genuine reasoning capabilities. At the heart of this investigation is the computational theory surrounding LLM reasoning, framed through the lens of the 3 SAT problem. The researchers emphasize the importance of phase transitions in LLM performance. Essentially, while these models can handle simpler problems quite well, they falter when faced with more challenging instances. This calls for a more structured approach to evaluating their reasoning abilities. To visualize the 3 SAT problem, the study breaks it down into clauses that are represented as disjunctions of literals. A key takeaway is the concept of phase transitions in random 3 SAT problems. Here, the probability of satisfiability shifts dramatically based on the ratio of clauses to variables, which directly impacts how well LLMs can reason and perform. The researchers pinpoint a critical threshold, around 4.267, where the performance of solvers like Mini-SAT begins to decline. This deterioration occurs because effective heuristics become less applicable, forcing the use of exhaustive search methods, which complicates the evaluation of LLM reasoning. Innovative methodologies are introduced for using LLMs as solvers for 3 SAT problems, particularly through formulations like SAT Menu and SAT CNF. Notably, the DeepSeek R1 model exhibits behavior similar to a metacoty, generating search trees that reflect its reasoning steps. This suggests that LLMs can indeed learn to reason, which could significantly enhance their performance in complex problem-solving scenarios. The study also reveals an inverted phase transition pattern in LLM performance on SAT problems. Accuracy tends to peak in easier regions, but drops sharply in harder ones. R1 stands out by outperforming other models, achieving higher accuracy in difficult instances, although it still struggles with completeness when it comes to finding satisfying assignments. When analyzing LLM performance against the satisfiability ratio, the researchers find that formulas with more satisfying assignments are generally easier for LLMs to handle. R1, in particular, maintains consistent accuracy across varying ratios, similar to classical solvers. It also demonstrates coherent search behaviors, employing strategies like tree search and backtracking, which enhance its reasoning capabilities. However, the study doesn't shy away from discussing failure cases for both DeepSeek R1 and GPT-4o. It highlights instances where these models misclassify satisfiable formulas as unsatisfiable. By categorizing model behaviors with color-coded boxes, the researchers shed light on heuristic selection, mistakes, backtracking, self-reflection, and self-correction, providing valuable insights into the reasoning processes and limitations of LLMs. Further examination of failure cases in DeepSeek R1's SAT Menu traces reveals incorrect satisfiability predictions due to overlooked clauses and flawed variable assignments. Interestingly, R1's reasoning process, which features a human-like narrative style, lacks the structured approach seen in SAT CNF, indicating challenges in generalizing across diverse input formats while effectively adapting reasoning depth. The researchers propose a hypothesis that training LLMs solely for longer chain-of-thought traces might lead to mere statistical pattern recognition rather than true reasoning. In contrast, R1's enhanced performance likely stems from reinforcement learning, which fosters more coherent thought processes. This distinction is crucial, as it highlights R1's ability to generalize beyond its training distributions, marking a significant advancement in the reasoning capabilities of LLMs. Next, we have the 8th paper to discuss. The paper titled On the Temporal Question Answering Capabilities of Large Language Models Over Anonymized Data comes from the AI research team at J.P. Morgan Chase. This study dives deep into how well large language models, or LLMs, can handle temporal reasoning using structured and semi-structured anonymized data that they haven't seen before. To tackle this challenge, the authors created a new dataset called the Reasoning and Answering Temporal Ability Dataset, or RATA for short. This dataset is crucial because it highlights that simply relying on LLMs alone isn't enough for effective and scalable temporal question answering. Instead, the researchers argue for a more integrated approach that combines various methodologies. One of the key contributions of this research is the identification of 17 different question types related to temporal reasoning. They also introduced an API that allows for external functions, which helps in building a robust temporal question answering dataset. The authors conducted experimental evaluations comparing different methodologies, including techniques like chain of thought and API access, to see how well LLMs can reason through various scenarios. The study also outlines essential algorithms that are vital for temporal question answering, such as sorting, counting, filtering, and interval duration. These algorithms play a crucial role in effectively retrieving and manipulating temporal data. Moreover, the authors introduced advanced techniques like chain of thought with self-reflection and external execution. A structured approach was proposed, utilizing predefined functions to guide LLMs through task analysis, function identification, and reasoning over results. This structured methodology significantly boosts their ability to tackle complex temporal queries. The evaluation phase of the study included 3 experiments that tested various techniques on the RATA dataset and other scenarios. They looked into how confident LLMs were in identifying temporal tasks and compared 6 different methodologies to assess their effectiveness in both structured and semi-structured data contexts. The results indicated that methods such as the chain of thought API significantly enhanced accuracy across various question types, especially in tasks involving temporal relations and event sequencing. This adaptability suggests that these methods can be effective beyond just the RATA dataset. Additionally, the study addressed the limitations of LLMs when working with larger temporal knowledge graphs and introduced a temporal confidence estimation technique that achieved 97% accuracy in distinguishing temporal reasoning tasks. This underscores the potential for developing specialized LLM agents specifically designed for temporal question answering. The CoTR method, which allows LLMs to revise their answers, showed promise, although structuring semi-structured data often led to poorer results. Ultimately, the most effective methods identified were CoTE and CoTAPI, which significantly improved accuracy, suggesting that a combined approach could be the key to scalable and reliable solutions for temporal reasoning. Now, let's move on to the 9th paper. This paper, titled Towards Quantifying Commonsense Reasoning with Mechanistic Insights, comes from a research group at the Department of Computer Science and Engineering at the Indian Institute of Technology, Kanpur. The authors are diving deep into the world of large language models, or LLMs, and how we can better understand their common sense reasoning capabilities. At the heart of their research is a novel graphical annotation scheme that leverages real-world activities to quantify common sense reasoning. They introduce the concept of scripts, which are essentially structured representations of implicit knowledge. This approach allows for a rigorous evaluation of how well LLMs can reason through common sense queries. The researchers have created a resource that taps into human crowdsourced knowledge to build directed graphs that represent real-world activities. This ambitious effort has led to the generation of an astounding 1017 common sense queries. This framework not only facilitates a thorough evaluation of LLMs, but also enhances our understanding of where common sense knowledge resides within these models, ultimately improving mechanistic interpretability. In their study, they conducted localization experiments using a method called Phi-2, which showed promising results while keeping computational demands reasonable. They meticulously analyzed common sense reasoning by annotating 40 daily activities, resulting in a comprehensive dataset that's now available on GitHub. This dataset is a treasure trove for researchers looking to explore LLMs' common sense reasoning capabilities through structured event alignments. To ensure the quality of their annotations, the researchers sampled trajectories from directed acyclic graphs, performing manual inspections to verify accuracy. Each trajectory generates common sense reasoning questions, and the compact graphs effectively represent the steps involved in various tasks. The queries produced have been validated by human annotators, showcasing high accuracy and significantly enhancing the evaluation of LLM's reasoning abilities. The paper also delves into the decision-making processes within LLMs, employing path-patching techniques to see how different prompts can sway model behavior. They highlight the importance of trajectory and choice set components in multiple-choice queries, revealing that even slight changes in how prompts are framed can lead to different predictions and reasoning outcomes. This insight is crucial for enhancing interpretability. Moreover, the authors introduce a method to analyze the direct effects of transformer layers on decision-making in LLMs using structural causal models. They stress the need for both clean and corrupted runs to understand how interventions on activations can influence outputs. A particularly interesting innovation is the introduction of conjugate prompts, which allow researchers to manipulate decision outcomes by flipping correct and incorrect options within trajectories. Through their experiments, they found that path patching has a significant impact on decision-making, especially after layer 20 of the model, where deviations in predicted probabilities become more noticeable. Layer 26 emerged as a key player in reinforcing decisions. Notably, the Phi-2 model outperformed larger models, underscoring the importance of model architecture in tackling common sense reasoning tasks. The authors also compare their directed graph approach to existing common sense knowledge resources like Atomic and Comet, which often lack the procedural structure needed for multi-step reasoning. Their method allows for extensive sampling of trajectories, addressing limitations in previous evaluations and providing a more robust framework for understanding common sense reasoning in LLMs. However, the study does acknowledge some limitations, particularly the reliance on just 37 stereotypical human activities for validation, which may not fully capture the breadth of common sense understanding. Looking ahead, the authors suggest that future work should explore a wider variety of prompt templates and delve deeper into analyzing attention heads, which could enhance the framework's utility for robust evaluation and circuit discovery in LLMs. Finally, we'll wrap up with the 10th paper. The paper titled Rethinking Theory of Mind Benchmarks for LLMs, Towards a User-Centered Perspective dives into a critical examination of how we evaluate theory of mind, or TOEM, in large language models, or LLMs. It's part of the Human-Centered Evaluation and Auditing of Language Models workshop at CHI 2025, and it pushes for a shift towards a user-centered approach in these evaluations. The authors argue that current benchmarks for assessing TOEM in LLMs fall short. They critique these existing methods for not accurately reflecting the complexities of human interactions, especially when considering neurodiverse individuals. This is crucial because if we want LLMs to be effective in real-world applications, they need to understand and engage with users in a way that resonates with their diverse experiences. One of the key points raised is that many of the current benchmarks only capture a narrow slice of what TOEM really entails. This limited perspective means we're missing out on deeper insights into how well LLMs can mimic human-like understanding. The paper highlights that many tasks used for evaluation lack what's called construct validity and reliability, which are essential for ensuring that these benchmarks truly measure what they claim to. Another significant issue discussed is data contamination. The training data for LLMs can muddy the waters when it comes to evaluating their TOEM capabilities. This makes it even more important to apply rigorous psychometric standards to these benchmarks, ensuring they are internally consistent and reliable over time. This way, we can trust that the measures we're using genuinely reflect LLM performance in real-world scenarios. The authors advocate for a redefinition of TWEM benchmarks that aligns with user-centered perspectives and empirical studies from human-computer interaction. They suggest that we should assess LLMs in dynamic social contexts, focusing on how well they can adapt and refine their understanding through ongoing interactions, rather than just measuring static inference accuracy. In a compelling conclusion, the paper emphasizes the need to draw from developmental psychology and existing literature on TWEM, particularly in relation to neurodiverse populations. This interdisciplinary approach is vital for enhancing LLM evaluations, ensuring they capture a comprehensive understanding of human cognition and social dynamics. Moreover, the authors stress the importance of employing diverse methodologies, including multimodal and multi-agent approaches, to better assess the social reasoning capabilities of LLMs. By integrating insights from recent studies, they aim to refine benchmarks that truly reflect the complexity of human-like interactions, ultimately leading to more nuanced evaluations of LLM performance across various contexts. Thank you for joining us on this episode of Momentum, Knowledge in Motion. We hope you found these insights into the limits of LLMs in common-sense reasoning tasks as intriguing as we did. Until next time, keep the momentum going.